Hello everyone. Today we'll learn about important theorems used in the electromagnetic theory, namely being Gauss Divergence theorem and Stokes theorem, followed by the basic equations used in the electromagnetic theory. Gauss Divergence theorem. It's a theorem which converts actually surface to volume integral and vice versa. So if A is a vector field enclosed in a volume V bounded by a closed surface S having continuous first order partial derivatives, then the volume integral of divergence of A dV is equal to surface integral of A dot n cap ds. What is n cap? It is a unit vector drawn normal to the surface S. So this is a conversion theorem. You will have to remember the theorem and we'll be using this result in further derivations. So the statement goes as the flux of a vector field A over any closed surface S is equal to the volume integral of the divergence of the vector field over the volume enclosed by the surface. The next very important theorem is called the Stokes theorem. If A be the vector field having continuous first order partial derivatives and S be an open surface bounded by a closed surface C, then the integral over C A dot dr is equal to surface integral of curl A dot n ds, where n is the unit vector drawn normal to the surface S and dr is the element of boundary of the surface C. A is A1 I cap plus A2 j cap plus A3 k cap. dr is the small element dx I cap plus dy j cap plus dz k cap. Now the statement for Stokes theorem is, it states that the surface integral of curl A over a surface S is the circulation or rotation of A around the boundary of the surface C. Now here you see basically Stokes theorem converts the line integral to the surface integral and vice versa. We'll be using this also. Now these are the common terms or relations used in this module. Uh, this is very important for you to understand this terminology. D is called the electric displacement vector, rho is the volume charge density, B is the magnetic flux density, J is the conduction current density, JD is the displacement current density, E is the electric field strength, H is the magnetizing field, sigma is the electrical conductivity, mu is permeability, epsilon is permittivity of medium, phi is magnetic flux or electric flux. So it can be phi E or phi M. Now the important formulae we'll be using, and some of these you already know, D is equal to epsilon times E, charge Q is equal to integral rho dV, B is equal to mu H, J is equal to sigma E, JD, this you will be learning short while. JD is equal to dou D by dou T, and electric flux phi E is equal to integral E dot ds. Magnetic flux is given as phi M equal to integral B dot ds. Now these are the basic laws of electricity and magnetism. The Maxwell equations. These are commonly known as the Maxwell equations. So the first Maxwell equation is called the Gauss Law in electrostats. Please remember now we'll be using two forms of these equations. One is called the integral form, which you people are already aware of, and this one is called the differential form, wherein we write these equations in the form of grad, divergence and curl operators. So this is actually the new thing you will be learning. So Gauss law in electrostats is integral d dot ds equal to integral over volume rho dv, or in terms of E you can write it as integral over surface E dot n ds is equal to q by epsilon naught. Second law is called Gauss law in magnetostats. Integral form is integral b dot ds equal to 0. Third form is called Faraday's law of electromagnetic induction, that is line integral of E dot dl is equal to minus integral dou v by dou t ds. The last law is called Ampere's circuital law. Now this is the older form. We'll be learning the new form also. That is integral h dot dl is equal to current enclosed by the path. These are all integral forms. Now similarly the differential forms are div d is equal to rho, div b is equal to 0, curl of E is equal to minus dou v by dou t, curl of H is equal to J. Now when we go for the modified Ampere's circuital law, which will be valid for the time varying fields, we'll be adding a new quantity called JD. Now we have to learn a very important equation which we'll be using to derive the modified Ampere's circuital law. This is called equation of continuity, or it is basically indicating the principle of charge conservation. Now this states that the total charge contained in an isolated system remains constant if no external charges are introduced into it. If the charge decreases in a given volume with time, then we can say that current is flowing, and the current is defined as the transport of charges in a given volume and is expressed as I is equal to minus dq by dt. Now this equation can be expressed in terms of current density, the conduction current density, which is given as integral j dot ds equal to I is equal to minus d by dt of, we substitute for q in terms of the volume charge density, that is integral rho dv, which is equal to integral dou by dou t of dv. There should be a minus sign here, where rho is the volume charge density and J is the conduction current density. Now we apply Gauss Divergence theorem to change the surface integral on left hand side into volume integral. Please remember, Gauss Divergence theorem was converting surface to volume integral. So on the left hand side we apply Gauss Divergence theorem. We get integral of divergence J dv is equal to minus integral dou by dou t of rho dv. So this equation becomes divergence of J is equal to minus dou rho by dou t. This can also be written as div J plus dou by dou t of rho is equal to 0. This equation is called equation of continuity. Now if you see carefully, for stationary charges or for the static field, rho is constant. So the second term becomes 0. If the second term becomes 0, then the divergence of J also becomes 0. So this indicates that the net outward flux of current density is 0. Now we'll be doing the derivation of these Maxwell's equations, namely Gauss law in electrostats, Gauss law in magnetostats, Faraday's law of electromagnetic induction, Ampere's circuital law or modified Ampere's circuital law after that. So let us first start with Gauss law in electrostatics. Gauss law states that electric flux through any closed surface is equal to the net charge enclosed inside the surface divided by permittivity of vacuum. Now this is the integral form. You people are already aware about this derivation, but we'll just go ahead with this again. So this is the surface. This is the surface element ds, and you see here n cap is this vector and electric field is in this direction. D omega is the solid angle. So we are deriving the integral form now. Let's consider a point charge plus q producing the electric field E. So this is the point charge situated at a point O within a volume enclosed by an arbitrary closed surface S. Let us consider a small area element ds around a point P on the surface where the electric field produced by the charge plus Q is E. E is along the OP direction, here it is, and area vector ds is along the outward drawn normal to the area element ds. Now the electric field strength E at a point P is given by E is equal to 1 by 4 pi epsilon naught Q by R square. Then the electric flux over the surface is integral E dot n cap ds is equal to Q by 4 pi epsilon naught integral S n ds by R square. Now what is this n ds by R square? This is called the solid angle. Now we know that integral over surface for the solid angle d omega is equal to 4 pi. So we'll substitute back for this into this formula and we get integral over surface E dot n cap ds is equal to q by 4 pi epsilon naught 4 pi. 4 pi gets cancelled. So we have integral over surface E dot n cap ds is equal to q by epsilon naught. Now this equation represents the Gauss law for electrostats for a single point charge. So if we have multiple point charges, we can keep adding up and we will have a summation of q by epsilon naught, or that makes it a total charge q by epsilon naught.